All right, so welcome to the last of MathStat 341 probability. So what I want to do is I want to continue what we've been doing for the past days, is just talking about applications of probability. So there's so many different choices of topics to do that it's always a challenge as to which ones do the best job of both showing what you can do with the subject as well as reviewing what you've done, not just in this class, but in other classes. And so this is one of my favorite topics. It goes back, or at least for me, it goes back to when I was an undergraduate working with a nuclear physicist for a couple of summers, leading into a thesis for my undergraduate and then for my graduate. And so the idea is to try to model a bunch of complex phenomena using mathematics. And it's amazing how many different systems can be described by the same type of mathematics. I have had a lot of Williams students over the summers investigate problems related to this. And so today we will see a lot of linear algebra, a lot of probability, a lot of combinatorics. Okay, so out of curiosity, how many people have taken a physics class? Excellent, so at least, an approximate majority. So the general problem is we have some system and we observe values at T1, T2, T3, and so on. And we want to figure out what rules govern the TI. So as a mathematician, I'll list a bunch of mathematical ones. Energy levels of heavy nuclei, eigenvalues of matrices, zeros of L functions, and so on and so on and so on. But you could look at a lot of other things. You could imagine that these are waiting times. So who might be concerned with the distribution of wait times? Chick-fil-A, restaurants in general. Who else? Okay, give me. So of any business, then anything you tell me should work. Customer service lines. So when you go to a bank nowadays, how many lines does a bank have? One, and it feeds into all the different tellers, so that as soon as a teller is available, next available person goes there. When I was young, each teller had their own line. You have the same average wait time in the two situations. Why would we switch? Lower variance. You could have that one customer who wants the special crisp bills and all these special blah, 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 and they're also depositing a bunch of coins, and they could just tie up a teller for a long period of time. Everybody behind that person now gets frustrated. So some people who had a really great wait time will have a slightly worse wait time, but that's fine, they're still gonna have a good wait time. But the people who would have had a terrible wait time are going to have a much lower one. And so it is far advanced, it's in a much better for the business to do something like this. Well, why don't we do this in supermarkets? Yeah, not enough space. But if you look at it, you have that small checkout area, and the small checkout area in a supermarket or a Walmart, you can't actually just have a bunch of people wait and the next one, because their stuff is basically limited to what they have in a small cart. Yeah, for the self-checkout lines. But you don't have as many people with large baskets, I think, coming out, because that would block too much of the space. But it's interesting watching how people maintain and manage lines. Disneyland is another great example of somebody who is very interested in spacing between events and modeling that. I remember when I went with my kids once, they gave one of my kids a red tag. And it was a really simple way to keep track of how long is it from that point in line until you get there, because they know exactly when they give you the red tag. And then when you get to the front of the line, they scan it. And so they give, it's almost constant feedback as to, it really is this long from this period onward. Very simple solution, but extremely powerful. So we want to try to figure out how can we use mathematics to understand diverse systems like this. And there's three general ingredients. The first is something we've been talking about all semester. We have to determine what is the correct scale to study the problem. When we're looking at the central limit theorem, it's not enough to just study a sum of a random variable. What's the right scale to look at it? Well, we often subtract off the mean and we divide by the standard deviation, so that the new sum that we're looking at now is going to converge to the standard normal. The next one is we need to develop an explicit formula relating what we want to understand, bless you, to something that we can actually understand. And so you have seen an example of this, or you should have seen an example of this in your linear algebra class. but almost surely it was not emphasized how important this result was. And at first it might just seem like, who gives a, but no, it's actually one of the most important results in linear algebra because it allows you to pass from something that you can work with to what you want to work with. And then the last is, in general, it is extremely hard to do any calculation exactly in mathematics. And if you write down a very complicated model, you're not going to be able to solve it. So you need to, in some sense, deal with averages. And again, this is where something like the central limit theorem kicks in. We saw the explicit formula for the density of the sum of 4 uniform random variables and how bad that is. And the goal is to approximate it with something else. And we want to do something like that here. So instead of calculating what's going on for a specific system, we will calculate what's going on average. And then we will pray that the specific system that we have is close to the system average. And frequently that is the case. All right, so just a quick review of linear algebra. This is one of the prerequisites for the class. We don't use it that often, but every now and then it's nice to have linear algebra. So if we have a non-zero vector V, it's an eigenvector of a matrix A with eigenvalue lambda if AV equals lambda V. So what that means is typically, a vector has magnitude and direction. When you apply a matrix to it, you typically change both the magnitude and the direction. If the direction is unchanged, we say it's an eigenvector. Eigenvectors are extremely valuable because if I keep applying the matrix again and again and again, it doesn't change the vector direction. So if I applied A n times, I would just get lambda to the n. Okay, absolutely wonderful. It turns out if your matrix A is real symmetric, we have what's called the principal axis theorem, that you can write any vector as a linear combination of orthogonal or perpendicular vectors. And you can do this for more than just real symmetric matrices. There's a whole class of matrices you can look at where you have this kind of decomposition. These are the good directions. If you think about an ellipse, the ellipse has the major and the minor axes. And if you have them aligned with the coordinate axes, then it's just x over a squared plus y over b squared equals 1. If the ellipse is rotated, then what you want to do is you want to rotate your coordinate axes. And then in the rotated coordinate axes, it has a nice formulation. Write it down like that, and then rotate backwards. It's effectively the same as just diagonalizing your matrix. Whenever you have a matrix is a representation of a transformation. Well, how do I represent a transformation? I'm writing down coordinates. So if I'm writing down coordinates, I have to have my vectors. I have to have my choice. And if I choose different vectors, I'm going to have my matrix looking different, but the physical transformation will be the same. So just for definiteness, if I give you the matrix 1, 2, 2, 1, if I take 1, 1, that's an eigenvector with eigenvalue 3. If I take 1, negative 1, it's an eigenvector with eigenvalue negative 1. All right, so probability density, and we've seen this numerous times, it's non-negative, it integrates to 1. The probability we take on a value between A and B is just the area under the curve from A to B. Standard ones that you could use: exponential, normal, uniform. We've all seen these so many times by now. Other ones that we might want to use is we saw the Weibel when we did sabermetrics. And what's nice about the Weibel is for special choices of the parameters, you can actually get the exponential as a special case. And so it's a more flexible distribution. And the more flexible your distribution is, the more things you can model by it. All right, so the key concepts is the mean or the average value of something, the variance or how spread out something is, the kth moment is just integrating x to the k. And the hope is that if your function is nice, then if I know the moments, I know the distribution. This is not always the case, but this is why we have classes like complex analysis to allow us to really prove what do we need to be able to uniquely determine the probability distribution. We won't worry about that. If I know that something is converging on average, that doesn't mean my sequence itself is converging term by term. So for instance, maybe I'm converging on average to 0, but half the time I'm 1 and half the time I'm -1. So nothing is actually close to the system average, even though the system average is what I'm converging to if I just do my running sum. So in terms of trying to show that things converge, it's not enough to show that the averages converge. If you can show that the averages converge and the variances tend to 0, then that will often be enough to show you that you do have convergence. All right, so what I want to do is I want to describe classical random matrix theory. This is a wonderful application of basic probability. All right. So how many of you have done, enough of physics to know about the difficulty of the three-body problem. Okay, so if you have just one point mass in the universe and nothing else, physics is trivial, right? If you have 2 point masses and nothing else in the universe, physics is still actually not so bad. If you have 3 point masses in general configuration, we can no longer write down in closed form what happens. And that's with just 3 particles. We can no longer write down the analytic solution. Now, if our models of physics are correct, there is an answer to how the particle behaves. We just can't write it down. So imagine how much worse it is when you have something like uranium with over 200 protons and neutrons and a much worse force than gravity. How the hell are we going to make any progress in something like this? Well, this goes back to one of the themes we've been seeing in this class, that if you can't exactly solve something, can you model it? Can you create some kind of random process that does a really good job? We saw this with 3x plus 1. And when we were modeling that by choosing the number of powers of 2 that we're removing as independent geometric random variables, the counts we got as to how many iterations we would need before we converge to 1 for our 10,000 digit number was almost perfect. And so it's a really wonderful idea of saying, I'm not going to try to solve the exact problem. I'm going to try to solve a related problem. So the way physics works is you shoot high energy neutrons into the nucleus and you see what comes out. The best description I've ever heard of subatomic physics is, imagine you want to understand how a grandfather clock works. So what you do is you take 2 grandfather clocks and you accelerate them up to 0.99 times the speed of light, smash them together, and you look at all the cogs and gears, or the remnants of the cogs and gears that spit out. And from that, you try to deduce how a grandfather clock works. This is how physics works. And amazingly, it turns out that there's analogs of this for number theory as well. That what I'm writing down for nuclear physics, you can actually do something very similar to this if you want to study zeros of L functions and stuff like that as well. All right, so the difficulty is in the lab, how do you actually do this construction? How do you actually accelerate things to be that speed? How do you smash things and actually record what's coming out? How many of you are familiar with Rutherford's gold foil experiment? So I believe a lot of his students were chosen based on a combination of eyesight and willingness to just stare at a screen for extremely long periods of time. It is amazing. We have a lot of rights that protect humans. Graduate students don't actually fall under those protections. There was one professor who had a theory that hunger was caused by your stomach expanding and contracting. So he took a grad student, a balloon, and an air hose, and he trained the graduate student to swallow the balloon and would inflate and deflate the graduate student's stomach while asking him, are you hungry yet? This is for science. They don't just let just anybody become a professor. All right, so so it is interesting as to just what you do, and then of course, can you trust the graduate student to say, what makes this stop? If you're familiar with Ghostbusters, you might think of Venkman's experiments in the beginning about psychic powers. So how do we do these experiments? Well, that's on the physics side of actually constructing the equipment that allows you to have things traveling at such speeds. On the statistics side, it is a tremendous amount of work to sift through the data that comes out and actually detect the small number of interactions. Because there are so few things that actually come out that are worth seeing to really advance the knowledge. It's a tremendous statistics problem. So the fundamental equation in quantum mechanics is H is your matrix corresponding to the Hamiltonian of the system. The psi n are the energy eigenstates. The En are the energy eigenvalues, or the energy levels. There are 2 things that prevent this from being solved or discussed in an introduction to linear algebra class. The first is H is infinite by infinite. And I believe most of the matrices you looked at were finite by finite. So that's the first difficulty. The second difficulty is we don't actually know any of the entries of H. So we need to diagonalize an infinite by infinite matrix without knowing any of the entries. Suddenly being the graduate student who has to swallow the balloon doesn't seem so bad. How the hell do you do this? Well, Wigner's great insight was basically to say, screw that. What I'm going to do is the following. Let's take a simple model and let's assume every molecule is moving either left or right at the same speed. And if I want to calculate some quantity such as pressure, I want to look and see how many molecules hit a wall in a given amount of time. What I can do is I can calculate this for each possible configuration. And for each configuration, I will see what the pressure is. And then I will average over all configurations. And then the hope is that the specific system I have is close to the average over all systems. And that's sort of like a central limit type result. That if you look at all the possible sample means you could have had, most of them are going to be quite close to the true mean, because we've normalized things appropriately. So most of them will be quite close to 0. So in nuclear physics, what we do is we choose a matrix at random, we calculate the eigenvalues, and then we choose another matrix at random and calculate the eigenvalues, and so on and so on and so on, and we average over all the matrices. And depending on the properties of your physical system, you look at different types of matrices. So you might look at real symmetric matrices, you might look at complex emission matrices. A lot of this comes down to what kind of time reversal symmetries does your system have. So if you've heard anything about like Noether's laws, about her great work, a lot of those invariants can come into play in terms of what matrices you choose here. Being a little bit more explicit, let's take a real symmetric matrix. So for real symmetric matrix, once I choose the main diagonal and the upper right, then the bottom left is filled in by symmetry. And so if I fix the probability distribution P, I can define the probability of my matrix as a product over the probabilities of each entry. I don't have to use the same probability for each spot. It just makes things a little bit easier. There's other ways to choose matrices at random, but this is a particularly nice one. Being very explicit, the probability I choose a matrix A, where the entry Aij is in the interval alpha ij, beta ij, would just be integrating from alpha ij to beta ij of the probability, and then I do this over all the different possibilities. So this is a nice probability space that we've very similar to stuff we've looked at. It turns out that if you require certain symmetries, it actually forces P to be a Gaussian. So should physics care how I orient my axes? The laws of physics should not change how I orient my axes, right? So if you put that in as an assumption, if you think about what a matrix is a transformation in a given basis. If I then look at my matrix and I diagonalize it, that's the same as essentially removing an orientation of the basis. And so when you diagonalize it, a matrix has n independent quantities, the n eigenvalues. And the other independent entries, so we have n plus 1 over 2 entries in this matrix. The other n minus 1 over 2 are actually what you need to uniquely specify an orthogonal coordinate system. And you're essentially saying, I want my physics to be independent of the orientation. So if I integrate out those choices of directions, I will get my n independent eigenvalues. I will get my n degrees of freedom. And so I want the probability of a matrix A and Q transpose AQ to be the same. Because Q transpose AQ is what happens if you rotate by an orthogonal matrix. Okay, well, if I take these probabilities and I require the probability of A and the probability of Q transpose AQ to be the same, when you unwind what that means, you get a differential equation and the solution is a Gaussian. This is similar to in standard integration, the integral we use, the dx, is invariant if we translate, if we replace the variable x with x plus 5, dx is still dx. It doesn't rescale at all. Okay. So we want to understand the eigenvalues of A because that's where the physics is. But it's the matrix elements that we choose independently. So does anybody remember the eigenvalue trace lemma? Anybody remember what the trace of a matrix is? It's the sum of the diagonals. So the eigenvalue trace lemma says that the trace of A is the sum of the eigenvalues of A, or more generally, the trace of A to the K is the sum of the eigenvalues to the kth power. And the last one is essentially trivial because you can show that the eigenvalues of A to the K are just the kth powers of the eigenvalues of A. The trace of A to the K is a polynomial in the matrix elements. Now that you've seen this on a slide, how many of you remember seeing this in a linear algebra class? That the trace of the matrix is the sum of the eigenvalues. This is one of the reasons why earlier in the day I gave you the matrix 1, 2, 2, 1 to calculate the eigenvalues. I know the product of the eigenvalues is the determinant. I know the sum of the eigenvalues is the trace. So I deliberately chose the matrix where I could quickly see what was going on. There were other nice things about that matrix. The sum of each row was the same as was the sum of each column. And if the sum of each row is C, then C is an eigenvalue, and just take the eigenvector 1, 1, 1, 1, 1. So it was not a random matrix for an example. It was a matrix where I was damn sure I was going to be writing things down correctly. Why is this so useful? Well, we want to understand the eigenvalues. That's where the physics is, but it's the matrix elements that we choose. And this allows us to pass from what we can choose to what we want. All right, so a little bit of probability notation. So delta, I can't remember if we've done this in this class. We used to represent a unit point mass located at x naught. So there are a couple of concepts that we just really don't want to define, and we just basically work under the assumption that everybody knows what we mean. So what does it mean to be a unit point mass? Anybody want to describe that? Anybody want to describe what a point is? A single location, no length, no width, no height. And so a point mass, has a mass of 1 unit, and all of the mass is concentrated at that point. So if you look at a plot of the density is 0 everywhere, except at that one point where the density is plus infinity. So it's equivalent of integrating a function that is 0 everywhere, but plus infinity at one point, and the area under the curve is 1. All right, so sometimes the way we do this a little bit more formally is what's called an approximation to the identity. What you can do is you can take a function which is very, very peaked over a very small window. And then you take the limit as it gets tighter and tighter and tighter. So one thing you could do is you could go up to height n, and you could be a triangle, and you could go from -1/n to 1/n. And then the area under the triangle would be 1. I'm sorry, would be 1. And then in the limit, it would be collapsing to all the masses at a point. Or you could take a Gaussian, and you could take the standard deviation of the Gaussian tending to 0, and then it would become more and more concentrated at the point. And this is extremely useful in advanced mathematics because now you're working with continuous differentiable things, and then you just have to worry about taking limits. Informally, though, screw that. Let's just say we've got a unit point mass. So all of the mass is at x naught. And so we're going to define this operator. So the integral of f of x against delta of x minus x naught is just going to return the value of f at x naught. It puts all of the mass at x naught. So I have a probability distribution. And so all of my probability is at x naught. So when I multiply it by f of x, the only thing that matters is the value of f at x naught. We can use this to build up a probability measure. So the measure is going to be the sum of point masses, not at the eigenvalues, but at the eigenvalues divided by 2 square roots of n. Well, if I have n eigenvalues, then that would give me a mass of n total. So let me divide each one by 1/n. So now the sum is going to be 1. So I now have a probability distribution. So I'm now putting a mass of size 1/n at each normalized eigenvalue. Which do you think really matters, the 2 or the square root of n in the formula? The square root of n. Why? Yeah, I mean, when I'm trying to see what happens as my matrix grows, as I get a larger and larger matrix, the square root of n is telling me what's the correct scale to study. This is one of the big themes of the class. What is the right scale to study the object? By dividing by square root of n, I'm going to get something that will converge as n goes to infinity. The 2 is so that I can say circle later in the day rather than ellipse. 2 is really not that important. And so if I want to calculate how many eigenvalues I have, how many normalized eigenvalues I have in the interval AB, I just integrate under the curve from A to B. And so since I have these point masses, every time I pass through one of the point masses, I get a contribution of 1/n. So it just counts how many normalized eigenvalues live in the interval AB. If I want to calculate the kth moment, all I would do is I would take that integral, and instead of integrating 1 times this, I would integrate x to the k, and now I would get the normalized eigenvalue to the kth power. Well, since I'm summing over all the eigenvalues, that's the same as the trace of a to the k by the eigenvalue trace lemma. And so all of a sudden, the kth moment, I can write it as a matrix polynomial, and it also equals the sum of the kth powers of the eigenvalues. Well, the sum of the kth powers of the eigenvalues is essentially the kth moment of the eigenvalues. I just have to divide by 1 over n. That's my extra, 1 from down there. If I know my moments, I should know my distribution. Well, if I have an n by n matrix, if I know the first big N moments, I should then know the eigenvalues. The problem is we have n going to infinity. And as soon as you have any infinity in mathematics, you have to be careful. And that's what makes the subject so challenging. Is for finite big N, if I know the first big N moments, I know the first n eigenvalues. Everything is fine. But in the limit as n goes to infinity, it's now a convergence issue. It's now delicate. You have to be careful. That's fine. Okay. So I want to talk a little bit about density of states. So the first big result in the field is due to Wigner. And what he proved is if you take a n by n real symmetric matrix, choose the entries independent, identically distributed random variables from a fixed probability distribution with mean 0, variance 1, and other moments finite, then as n tends to infinity, the density of the normalized eigenvalues converges to a semicircle. As you go deeper in mathematics, you can play a game. It's sort of like, how many of you have ever seen the TV show Name That Tune? Where you have to say how many notes do you need before you can correctly name that song. Here it's, what's the weakest condition you need to be able to prove the theorem? This is not the weakest condition by far. Typically, I think all you need now is like the third plus epsilon moment to be finite. You don't need all the moments to be finite. But as soon as I tell you all the moments are finite, what might you be thinking about? Well, that's a specific distribution. As soon as I tell you all the moments are finite, what might you think you might be able to use? Not central limit them. What function do we have that might become available if the moments are finite? The moment generator function. Now, it might not be enough that the moments are finite. I might need some growth rate on the moments. But as soon as you hear that, you might be thinking, okay, well, maybe some of those techniques now will be available. And depending on how rapidly things grow, you might have some difficulty in terms of what can and cannot be done. Okay, so let's get a sense of the correct scale. The trace of a squared is the sum of the eigenvalues squared, but the trace of a squared is just the sum of aij, aji. And this is a nice calculation. If I have a squared and I want to calculate the diagonal entries of a squared, this is what I get. Well, that's the sum of aij squared. Each aij is chosen from a distribution that has mean 0 and variance 1. So if I look at the expected value of aij squared, since it has mean 0, it's the same as the variance. So that's 1. What's the expected value of a sum of independent random variables? It's the sum of the expected values. So again, another chance to review what we've been doing. So I would expect that sum to be of size n squared. So I expect that the sum of the squares of the eigenvalues to be of size n squared. For real symmetric matrices, it turns out that all the eigenvalues are real. So I don't have to worry about any cancellation in sign. So if the sum of the squares is of size n squared, then that means each one on average is going to be of size square root of n. Because I have n terms, and if I sum the n terms and I square each one of them, if each one is root n, this would be of size n of them would be n squared. So this suggests that the correct scale to study the problem is to divide by square root of n for the eigenvalues. Okay. And so now we want to calculate what are these average moments. And so to calculate the average moments, I put in the trace of a to the k with all the crap below. I multiply by the probability I chose that matrix, and then I just do the integration. All right, that's going to be a bit of a challenge. The bigger the polynomial is, the harder this integral might be to do. But it turns out that there are actually very good techniques to do this. And we're going to look at what happens in the limit as n goes to infinity. So we don't need to calculate things exactly. All we have to do is determine which things have a finite limit as n goes to infinity, and which things instead go to 0. So for instance, if I can show something is bounded by, n to the k fourths, great, I'm dividing by n to the k halves plus 1, that's going to go to 0. So I don't have to figure out exactly what it is. So one of my advisors called this counting on fingers, is you don't have to evaluate it exactly, you just have to do enough to figure out, is it going to survive in the limit? We saw this when we were doing the proof of the central limit theorem. And again, the goal of today is not just to show you good math, but to review what we've done throughout the semester. When we did the central limit theorem and we did the expansion, oh Lord, remember we had that massive product. We used the moment generating function of a sum is the product of the moment generating functions. We took logarithms. We then Taylor expanded the logarithm. And then we said, well, when we multiply everything out, we have n times the log of the moment generating function of one of them. We don't have to keep too many terms in the expansion because eventually they're so small that in the limit they go to 0. But if we wanted to talk about how fast something converges, that's where we would get the result. And that's where we saw that the universality in the central limit theorem came from the fact that we can always adjust a nice distribution to have mean 0, variance 1. But once we do that, we have no more degrees of freedom. We have no more freedom to change. And so the third moment, or the fourth moment if it's symmetric, is the first moment that shows the shape of the distribution. And that's going to control the convergence to the central limit theorem. That's going to control the convergence to the Gaussian. It's the same here. The moments and whatnot will control how quickly it's converging to something, but not whether or not it converges. And so if you look at the whole family of real symmetric matrices, it turns out that the sum of the kth moments is going to converge to the Catalan numbers if you've ever heard of them. This is the number of ways to legally put down parentheses. It's the number of paths from the bottom left to the upper right where you don't cross the main diagonal. And then you have to do some technical stuff. You have to control the variance. It's not enough to just show that the average value converges. We talked about, well, what if you're 1 half the time and minus 1 half the time? But if you can show that you're converging on average and the variance is tending to 0, then that's enough to show convergence. And so, for example, let me give an extremely misleading case. Let's look at the special case when we're trying to calculate the second moment. So we have, a ij squared. And then when we look at it, well, because it's the second moment, I only have one term in my expansion for the trace of a squared. So when I look at all the integrals, all of the integrals are just integrating the function p with a integrand of 1, except for one special variable where I have aij squared. Well, that's just the formula for the variance, which we know is 1. And what do all of these integrals equal? So we're integrating our probability distribution from minus infinity to infinity. Just 1, because it's a probability distribution. So this is 1 because it's a probability distribution. This is 1 because it's the variance. And so we just get 1. So the second moment is actually very easy to calculate. Well, what would happen if you had a higher moment? Well, if you had a higher moment, it would be a little bit more involved. I think I have those. Oh, okay. I guess I did not decide to do those here. I'll show those later, I guess. Okay. So here's an example of choosing 500 matrices. Each matrix is 400 by 400. The entries are chosen from a Gaussian. If you have decent vision, you can see that there is a red line that's going around over here. And that is the theoretical semicircle prediction. And you can see phenomenal agreement with the theory and experiment. We're looking at the normalized eigenvalues. They essentially live between -1 and 1. And notice that for the histogram, we've adjusted it so that you can read off probabilities. I'm not doing number of counts. I much prefer to have probabilities rather than number of counts. So the Gaussian is a great distribution to choose. Clearly, mean 0, variance 1, finite higher moments. I know some of you are troublemakers and sometimes do not like being told what to choose. So what distribution would you like to try next? You don't have to satisfy the conditions. Well, you don't, yeah. Well, we know if it satisfies the conditions, it's going to be a semicircle. Yeah, take the Cauchy, right? What would happen if you take the Cauchy? Right? And so here's the Cauchy distribution. So very non-semicircular. Now, if you look at this, You know, almost looks like an X-wing coming in. That is not, I'm sorry?
Oh my God, it does.
It does look like an X-wing. There is actually the Batman distribution. There is a distribution where the distribution of eigenvalues actually looks like Batman.
Do you have it on the slides?
I don't have it on the slides, but if somebody sends me an email, I will find the Batman distribution. I have the CBS or the Saturn, I have the Mickey Mouse. Those ones I discovered with my students. Someone else discovered Batman. I was going to say, what color do you have to plot Batman in?
Kind of black.
Or really dark gray in honor of the Lego movie.
Very, very dark green.
So the person who owns the movie rights to Batman, Michael Uslan, came to Williams a few years ago. And I am happy to talk about, you know, you read his graduation speech. Phenomenal person, absolutely phenomenal. Do you think that there's really this much of a spike at 300? What do you think this represents? Yeah, everything from here onward. Yeah, it doesn't just spike up like that. Well, the thing is, the problem with the Cauchy is it has very slow decay. So you're not surprised that it has a huge amount from some point onward. So if the conditions are violated, you can get very different behavior. What's fascinating and still unproven is if you look at more interesting refined properties, such as the spacing gaps between eigenvalues, you actually seem to see the same thing for Cauchy as you do for Gaussian. That the spacing statistics is more universal, but the count statistic is a little bit more varied. So what I want to talk about for the last bit of class is how if we put in different structures on matrices, we can see different patterns. And this is where you're going to have an interplay between combinatorics, probability, linear algebra. The different families of matrices will have different behavior. And part of this is talking about how do you make conjectures. And I will talk about a wrong conjecture that I made with some students. All right. So a Toeplitz matrix is a matrix of the following form. So it's constant along diagonals. So a real symmetric Toeplitz matrix, B minus 1 would be the same as B1. So if I give you a real symmetric Toeplitz matrix, you might as well make the main diagonal 0, because all the main diagonal does is it's just B naught copies of the identity. So it just shifts all the eigenvalues by B naught. And so we have n minus 1 independent parameters. On a generic real symmetric matrix, I have n plus 1 over 2, basically order n squared independent entries. So a Toeplitz matrix has far fewer independent degrees of freedom. So the hope is, because it has fewer degrees of freedom, you might be able to see some very different behavior. So you always have to be careful about making inferences from small sets. One of the goals is that we want to try to find interesting behavior. The larger the space you're looking at, the harder it's going to be to see the truly interesting thing because it's going to be drowned out. And so we want to work with small families so that we can hopefully see something new and interesting. But the difficulty is if the family is too small, we might not actually be able to do the averaging and do all the integrals. So it's a really nice balance between the two. We want the smallest family we can take where we can still actually do the calculations. And so, you know, exactly as before, we form the spacing measure. So we put a massive size 1 over n. Now we just normalize by square root of n rather than 2 square root of n. It's the root n that matters. The kth moment is just going to be the trace of a to the k. And then we want to calculate what is the limit as n goes to infinity of the average kth moment. The same calculation we did as before shows that the second moment is 1, and it's not hard to show that all the odd moments is 0. And the reason is the following. When you look at the trace of a to the k, it's going to be an expansion in terms of the matrix elements. What are we assuming about the probability distribution? The probability distribution has what properties? Finite moments. What else? Integrals 1. What else? We're not assuming non-negative. Nope. Mean 0. So if we expand the trace of a to the k, if k is odd, then we either have one of the entries is unmatched, or there has to be a triple matching. You can't have everything just matched in pairs. If you have something that's unmatched, well, since the expected value is 0, you get 0. So everything has to be matched in at least pairs. And this is the counting on fingers argument I was referring to earlier. You can show that if there's even one triple matching or higher, that when you divide by n to the k halves plus 1, it goes to 0. That the number of tuples with a triple matching or higher with everything matched in pairs is so small that when you divide by n to the k halves plus 1, it goes to 0. So all the odd moments trivially vanish because you either have something unpaired or too much is paired. So we only have to deal with the even moments. Okay. And so because it's a tuplets matrix, rather than writing Ij for the entries of A, I'm going to write B of the absolute value of I1 minus I2. That's going to just tell me which diagonal I'm on. So if I1 equals I2, I'm on the main diagonal. If it equals 1, I'm either above or below the main diagonal. And so when I have something like this, everything has to be matched in pairs. And so if two things are matched in pairs, there's two possibilities. If I look at the indices, either they're the same when I look at the difference, or they differ by a factor of -1. There are 2 to the k choices of sign because I have k pairs because I'm doing the 2kth moment. So I get a factor of 2 to the k from the choices of sign. How many ways are there to take 2k objects and match them in pairs? 2k minus 1 double factorial. It's on the board, right? Where have we seen 2k minus 1 double factorial before? Yes, it was on a homework. On midterm, I love 2k minus 1 double factorial. It's one of my favorite double factorials. So what? Well, look, we're calculating the 2kth moment. And one of the things that's coming out of the 2kth moment is the 2k minus 1 double factorial. Any distribution whose 2kth moment is 2k minus 1 double factorial. Gaussian. Which Gaussian? The standard normal, its 2kth moment is 2k minus 1 double factorial. So what this tells you is if everything contributes maximally, you would get 2 to the k times 2k minus 1 double factorial. It turns out doing some linear algebra, the only choice of sign that works is when it's always the minus sign. So of the 2 to the k possibilities, only one survives. And the moment is going to be bounded by the moments of the Gaussian. And so I'm not going to go through the linear algebra calculation, but by doing some linear algebra, you can show that the only contribution occurs when you always have the negative sign. And so we get that the 2kth moment is at most 2k minus 1 double factorial. So it's bounded by a Gaussian. And so we thought initially that it might actually be a Gaussian, and we had some heuristics and some numerics as to why it should be a Gaussian. It turns out it's not. So let's look at the fourth moment. So there are 3 ways to match things for the fourth moment. We could match with your adjacent neighbor, and there's 2 ways to do that. I could match to the right or match to the left, or I could match with your opposite. Do we agree that the left and the right are the same? Just take a mirror. So it turns out the left and the right both contribute 1. And so the fourth moment of the Gaussian is 3. They both give you a 1, but the middle one does not give a 1. It gives a little bit less. And so when we do the adjacent matchings, it turns out, if we want I1 minus I2 to be negative I2 minus I3, and the same for the I3 and I4s, you very quickly get, oh, well, look, they both have an negative I2 that cancels. I1 equals I3, and I2 and I4 are arbitrary. So what that means is I can choose I2, I4, and I1. I3 is determined. I have n cubed tuples. I have to be a little bit careful because I don't want them to be the same thing. I don't want a quadruple matching. But I basically have n cubed tuples. I divide by n cubed, that gives me 1. If I look at the other case, case 2, I now have I1 minus I2 is minus I3 minus I4, and the next equation is the same thing. And so you now get I1 is I2 plus I4 minus I3. And that has an obstruction. So if I2 and I4 are both large, say they're both 2/3 n, and I3 is small, say it's at most 1/3 n, then this would be at least 4/3 n. And you'd be subtracting off at most 1/3 n. So this whole thing would be greater than n, and that's too large for I1. So that's enough to prove that we lose at least 1/27 of the tuples. You can do a better job and count exactly how many there are. So this is enough to show that it's not going to be a Gaussian, it's going to be a little bit less. And so you get 2/3, not 1 for that last contribution, you get 2 2/3. I could have structured this lecture differently. If I asked you, what do you think of when you see this curve, what would you say? Gaussian. Now that you know that the moment is a little bit smaller, how would you adjust? What do you say? What do you see now?
Pretty much there.
Pretty much a Gaussian. Does this look like it's decaying faster than a Gaussian or slower than a Gaussian? Faster. The moment's smaller, right? And, oh yeah, see, it's falling down a little bit too quickly. And so this is the danger of when you know what the answer is, you can adjust how you do things. Did I share with you the Asimov article, The Planet That Wasn't on Vulcan? All right, I will share that. It's a great example of bias in science, where if you believe you know what the answer is, and some data can be looked at multiple ways.
The one where they thought there was another planet.
Yes,
Mercury,
yes,
and all this.
yeah, a planet between the sun and Mercury. And the person who was proposing this was the person who had found Neptune. And so he was the first person to mathematically predict where a planet should be. This was the equivalent of the rock star in the 1800s. And so was listened to quite well. So when you look at this, you can easily think, yeah, this could be a Gaussian, this could be some errors of small size. And that's the danger. So we proved that it converges to a new distribution, which is not quite a Gaussian, but is close. If you change the matrix by adding a little bit more structure, if you make the first row a palindrome, so instead of going, B0, B1, B2, all the way up to Bn minus 1, if you go B0, B1, B2, ... B2, B1, B0, if you do that, then all of a sudden it becomes a Gaussian. And the reason is now you have a little bit of extra freedom in terms of trying to do the matching. And that little bit of extra freedom is enough to balance everything. So what I want to do for the very last bit is just really quickly talk about some other ensembles of matrices. This is the block circulant, where we now have wrapped around diagonals, and they're periodic with period m. So if the period m is 1, it's going to essentially be very similar to a toplets. If the period is equal to n, then it's going to just be a real symmetric matrix. So this is in some sense a matrix family where we can change the structure. We can interpolate in some sense between toplets, which has n degrees of freedom, and real symmetric, which has n squared degrees of freedom. And so I'm not going to do all the calculations. It turns out things again have to be matched in pairs. Has anybody here taken topology? All right, so I'm not going to say too much about this, but if you've taken topology, you might have seen figures like this where you glue things together based on how the arrows are. If they're pointing like this, you glue them together, otherwise you twist them. And it turns out that this is related to the genus of the different shapes you get when you glue together. And so I won't go through all the details. Today, you can actually get an explicit closed form expression for the characteristic function, which we know is the Fourier transform. And so we can actually invert this and we can get an explicit formula for the density. So if it is periodic with period m, if m equals 1, it's going to essentially just be our Gaussian. And as m gets larger and larger and larger, it's not clear that this converges to a semicircle, but it does. And if you start looking at the data, here is looking at a plot when m equals 1, and you can see that it looks very much like the Gaussian, a lot more probability beyond the -2. You're not going to be fooled again. And you can see a wonderful fit. This is m equals 2, m equals 4. It's really picking up the different structure. I'll just jump ahead. Here is the limit, the semicircle, and you can see that as m is getting larger and larger and larger, it's getting very tight about the semicircle. The last one is I don't have the Batman distribution, but I do have the checkerboard. So every, so many steps, we repeat a W. What do you think W stands for? I'm sorry, not? At least two of you, by what you're wearing today, should know what W stands for. Williams. Now, of course, we can't say that in a paper. So W stands for weight. So, use. No. Oh, well.
The very world is collapsing right now.
Oh, I see. Well, yeah, because there's a default to do red rather than purple. And so you could ask, well, what would happen in a situation like this? And so we end up getting a split distribution where almost all the eigenvalues are concentrated over here besides root n. And if it repeats every k, you get k eigenvalues that are larger. The problem is this is enough to destroy the method of moments because the small number of moments here are enough to completely overwhelm in higher contributions. And you can see it goes further out. I will just end up with the pictures. No, I guess I don't have those pictures here. This is close to, you're getting towards the Batman, but you can see a little bit of the hood. There's a much better one than this. This is not the Batman. I will get to the Batman. All right, it has been a lot of fun doing probability. If